Yeah, I guess so. Make sure I'm recording here. Yeah. Okay. All right. So we talked already last class about antiderivatives, right? Yes. I even gave you some notation. So we'll get back to that. But I wanted to just kind of step back for a second and make sure we had the definition. By the way, the projector is still out of order, and I've been told that they have a ticket in to get it repaired, whatever. Something about that wall plate over there is not working, whatever. So hopefully next week we'll have the projector so we can look at the notes instead of me just having to write them up here. But the definition of an antiderivative of a function is, so if somebody gives you a function, right, and you want to find an antiderivative, it's any function. I should put here any function, so long as it satisfies this equation, that the derivative of that function, capital F is what we're going to call it. That's the antiderivative. As long as the derivative of that is little f, right? An example of that would be if we have little f of x is 2x, then obviously capital F of x being x squared is an antiderivative. But it is not the only one, right? We talked about that last class, that you could basically take that and add any constant to it, right? So some other examples. I'm going to call this capital F sub 1 is an example of an antiderivative, right? But if I wanted to come up with another example, all I'd have to do is just add a number to it, right? And that would work. And then I could, makes no difference if I subtract a number. How about pi? Pi is a number. That would still work, right? So I could go all day long, right, coming up with examples. Basically, they all have the same characteristic. The characteristic is that you have x squared plus some constant. And this right here is referred to as the general antiderivative. All right, it's the general antiderivative. Now, to get the general antiderivative, we know that we can add a constant because when we differentiate it, it goes away, right? But we can't do anything else because it would change the derivative. Like I couldn't put a number in front of x squared, right? Because then the derivative would not be 2x. Like I couldn't put 5 in front of this. I couldn't add another x out here, right? Because then I would take derivative and I would have like a plus 1. So the most I can do is add a constant, right? All of these graphs, right, or all of these functions all look similar to one another, right? What are they? What are all these graphs? If I asked you right now to graph capital F sub 1, what would it look like? It's a parabola, right? And it passes through the origin. So this would be capital F sub 1. And then what about capital F sub 2? Just that up 4, right? So it would look like, I don't know, like this. But it would be the exact same shape, right? Just moved up. And then if I said minus pi, well then, that one would be down 3.14, somewhere around there. Oops, I missed it. That's the lowest point. Okay, so that's capital F sub 3, right? So what we have is, if somebody gives you a function, little f, and we try and find a specific antiderivative, then we can get specific ones. But in general, all of these live in a family, right? They all it's like a family of answers, all right? Use the word array. It's kind of like an array of answers. There's not just one, though. It's an infinite number of them, right? But they all have something in common. So here's what they have in common. If you were to take some point, let's just say I pick some x value. Let's just call that x value a, all right? In any of these functions, if I take the derivative, this is a terrible green. If I take the derivative of f sub 1, right, this one, and I plug a into it, that's going to give me a slope of a tangent line, right? It's going to give me the slope of the tangent line of this graph, of this black graph right here, right at this point. It's going to give me the slope of that tangent line, isn't it? Now, what is that slope going to be? Well, the derivative of this is 2x, right? So If I plug a into that, I get 2a, right? So I get 2a here. But that would have worked for all of these. So if I do capital F sub 2 of a, take the derivative, sorry, then I would take the derivative of this, which is still 2x, then plug in a, I get 2a again. So that means if I go to the second function up here, go up to a, look, these are parallel, right? And that would have worked for all of these. So as you move through from left to right, if you pick points and look at the tangent lines, they're all going to be parallel on any of the graphs, any of the antiderivatives from the family. Got it? Okay. All right, so we did discuss that a little bit last time, right? And we started to come up with this thing called the power rule, and then I showed you some notation, right? But I want to take kind of another step back, and I want to talk about some of the antiderivatives that we already know. Okay, we walked into this class and we actually knew some antiderivatives already. So here are the known antiderivatives. And unfortunately, right now, our list is pretty small. So let's start with some that I'm pretty confident you're going to know. If I give you that little f of x is cosine x, then what would the general antiderivative of this be? Sine x plus c. So from this, capital F of x, the general antiderivative would be sine x plus c. And you know that because you know the derivative of sine is cosine from Cal 1, right? All right, let's see if we can do this for sine. What if little f of x was sine x? Then can we come up with the general antiderivative for this? It would have to be negative cosine, right? Because if it's just cosine, the derivative of cosine is negative sine, so we don't want that because we want it to turn out to be positive sine, so we would have to put negative cosine x plus some constant. Right, so we know these because of our experience in Cal 1. Now, I've taken, if we look at just the pre-cal trig functions, right, sine, cosine, tangent, if I put tangent here, that's the derivative of it though, right? Mm-hmm. So if I put tangent here, what do you take the derivative of to get tangent? And that is not something we know, right? We know the derivative of tangent is secant squared, but we don't know backwards, right? So we can't do tangent, but we can do secant squared, so that's a known one, right? So look, check this out. I could put secant squared here, secant squared x. If I'm trying to find the antiderivative of secant squared x, I know that tangent x plus c will work, right? Could I put just secant here? The antiderivative of secant. Do you know from Cal 1 what you take derivative of to get secant? No, right? Now you know the derivative of secant. The derivative of secant x is secant x tangent x, right? So we could put that here, right? You see, we're very limited right now. Secant x tangent x, we can put that here because we know from Cal 1 that the derivative of secant x is that. Does that make sense? Just going backwards from Cal 1. I knew the derivative of this was this. And there's a few more I could do, right? There's two more, right? You know the derivative of cosecant x is negative cosecant x cotangent x, and the derivative of cotangent x is negative cosecant squared x. Anyway, these all appear on your formula sheets, all right? But the point of this is just to illustrate that right now we have a very small group of functions that we can find antiderivatives of, right? Okay, let's switch away from the trig functions. How about this one? How about if f of x was e to the x? How about an exponential function? How about that? Do we know the antiderivative of this? It's itself, right? E to the x plus some constant. That was a real nice one. Hopefully your Cal 1 instructor really showed you just how awesome it is that the derivative of e to the x is itself. All right, so we have that. And then e has an inverse, right? The exponential function, e to the x, has an inverse, the natural log function. And the derivative of the natural log was what? 1 over x, right? So I can put that here. So like if I ever see 1 over x, I know that that is ln x plus c. Now your book is most likely going to put absolute value around the x when you do an antiderivative because domain restrictions on the log function, you can't plug negatives in. So you may see that in your formula sheet. Okay, so just keep in mind that with all of these, each time we find the general antiderivative, we have an entire family of functions. And each one of these is a different family, right? Okay, and then what we talked about last class is that if we have x to any power, we have a way of going backwards, right? So this is what we call the power rule. The power rule says that if little f of x is x to a power n, then the general antiderivative of this was 1 over n plus 1 x to the n plus 1 plus some constant. Y'all have that in your notes from last time, right? Okay. Now this worked almost all the time. There was one case where it didn't work, remember? This only works so long as n cannot be negative 1. But that's okay, right? We're not too concerned about that because when n is negative 1, this is really 1 over x, and we knew that it was natural log. So in other words, we have a way of finding the general antiderivative of x to any power. All right? And then the last thing from last class is instead of sitting there and having to tell you over and over, find the antiderivative of this, find the antiderivative of this, find the antiderivative of this, we have notation that we use. And the notation that we have is that if you write this symbol, which is known as the integral, okay, then you put the small f in here, and then you put this little dx. That dx is called the differential. And by the way, the function you put in here, we call that the integrand. Then basically, if you ever see this, it's saying to go find the general antiderivative. That's what that means. It says, look at that, give me the general antiderivative. So this is capital F of x plus c. So some things about this notation. This symbol I will explain later in more detail when we start to get into something else, just not yet. And then this little differential thing, it actually has a very, very important meaning for us, all right? But for now, I just want you to think about it this way. All this does is keeps track of what your independent variable is. So in this function, do we all agree that x is the independent variable? Like that's the one that I guess you could say is getting plugged into the function. This right here keeps track of the variable you're treating as the independent variable. Now you may be like, well, duh, it's obvious. I could have just wrote that. I know the independent variable is that, right? Yes? But like in a Calculus 3 class, you may have 3 variables. And when you're trying to find the antiderivative, you might have to be very clear on which variable you're treating as independent versus dependent. And so this keeps track of it. And later on, it will have a nice geometric meaning. But I just want us to understand it very simply today as this means go find the antiderivative. All right?
So if you put it for like y, would that be like
dy?
Would that be like implicit?
It's kind of, yes, like implicit. You have to treat one thing like a constant and the other one not. That's basically what would happen. If this was a function of x and all there were in here were x's and numbers, then if this was dy, then you would treat that like a constant and you would just basically pull it out and integrate. You would take the antiderivative of 1, which would be y, because this would be y here. We'll get to that. Don't worry about it. Yes?
So when you're writing out your steps, you need to show dx?
You always show dx. Yes. Yep. I just, students always say, like, what is that? And I'll show you what it is. We're just not yet, because it'll bog us down with other things and your mind will be in like two different places. I want us just to be thinking about, let's find antiderivatives right now, okay? But it turns out it's got a great, great geometric explanation as to what it is. Okay, that's it. That's kind of a summary of last class at the end, the last 10 minutes. And then this is kind of like the stuff we already knew walking in, but we're just kind of thinking about it again. Yes? Let's do a couple of examples. What I'm mainly going to be doing here with these examples is working this power rule a little bit and just making sure we're all comfortable with it. So how about this? Here's an example. I want us to find the antiderivative of x squared minus 3 square roots of x plus 4 cube roots of x minus 5 seventh roots of x to the 4th. Okay. So we're kind of jumping in here. Now, I'm not done writing out the problem, right? What am I missing? I'm missing the dx, all right? And also, just to be very clear, I'm going to put all of this in parentheses. This is the integrand, okay? This is the integrand. This is this. So we want the antiderivative of this, and x is our variable, right? All right, now do you remember in Cal 1 that when you took derivatives, that if you had addition and subtraction, it was great because you could just take derivative of each one and then just add and subtract them? Well, the good news here is that it works the same way with antiderivatives. So you can take the antiderivative of each of those independently of one another, all right? Now, if we wanted to be really technical, we could write, okay, we want the antiderivative of x squared dx minus the integral 3 root x dx. Don't write this down unless you really want to. But you see what I'm doing? I missed my dx here. Okay, that's what I'm saying. You can do each one of these, like find the antiderivative of this, then subtract that one, then add that one, and then subtract that one. You see? But I'm not going to write that all down. I'm just going to kind of do it all at one time. Is that all right? Now, bless you. The only thing that we can do in these problems is use this rule. And the reason why is because everything you see up there is a power of x. Do y'all agree? So let's first, before we do anything, convert all of these over to what we would refer to as rational exponents. So instead of radicals, we use rational exponents. So this is going to be x squared minus 3, and then what? X to the 1/2, and then plus 4x to the 1/3, and then minus 5x to the 4/7 dx. And if you need a quick reminder about radicals, the nth root of x to the m is x to the m over n. All right? That's what I'm using there. And now we have 1, 2, 3, 4 terms. Each of them has x to some power, right? So this one has an n, that one has an n, that one has an n, that one has an n. And then what about these numbers in front, like the -3 and the +4 and the -5? What do you think happens with those when I take antiderivatives? They just come with us, right? It's just like when you took the derivative, like if I had 4 sine x, right? And I say take derivative, you're going to say 4 cosine x, right? You just brought the 4 with you. Okay, so that's what's going to happen when we do antiderivatives. The constants are just going to come along. All right, so let's try and do this. Now watch on my next line, I'm put equals, and now I'm no longer going to write the integral sign because I actually am taking the antiderivative. I'm finding the function. So this is going to go away, and this is going to go away. My answer is just going to be capital F. So looking at this first one, n is 2, right? And we're going to use this formula. So it's going to be 1 over 2 plus 1, x to the 2 plus 1. Yes? All right, so I think that one's pretty clear, but I'm going to write it out in detail. This is the first example. I'll write it out in detail. I know that you can add 2 plus 1. Okay, but that's the formula, right? That's this. And then I have minus 3. I just write it down, and then times. And now I have this one, and I'm going to use n is a half. So it's 1 over 1 half plus 1, x to the 1 half plus 1. Were there any questions about that formula? Because we did cover it at the end of class. Y'all are okay with it? Okay. What next? Plus 4 times, now we're using n is 1/3. So 1 over 1/3 plus 1, x to the 1/3 plus 1. And one more, minus 5 times, and now n is 4/7. So 1 over 4/7 plus 1, x to the 4/7 plus 1. And I did forget one last thing, plus c. Sometimes students will ask me, they'll be like, yeah, but you know, like what happened to the dx? If it makes it easier for you, just say that the dx turns into the plus c. That's not what happens, but that'll help you maybe not forget the plus c, all right? So like the dx becomes the plus c. All right, we good? Now you get to add fractions, right? Which is, you know, one of your strong suits. So when you add fractions, we know how to do that. You need common denominator and all that. We're going to be adding 1 to fractions a lot. Okay, so that's just something you're going to get have to get really comfortable with. So just remember, if you're going to add a fraction, let's say you have like 2/3 plus 1. Anytime you do that, you're just going to rewrite 1 as 3 over 3, right? Common denominator, and then just add across. All right, so let's go ahead and get this. I'm going to leave that one. I'm going to leave that one there. I want to leave this one. I'll leave this one on the board. Okay, so let's see. What do we get here? This is equal to 1/3 x cubed. Okay. Minus 3 times. Now, 1 half plus 1 is 3 halves. And 1 over 3 halves flips it over and becomes 2/3. So this is 2/3 x to the what? 3 halves. See, we did this computation twice, right? It's the same number, except because it's 1 over it, we get the 2/3, but this is actually 3 halves. That will always happen. Whatever this exponent is, this in front of it will be its reciprocal. Okay, now next one, plus 4. And then we have times, and then here, 1/3 plus 1. 4/3, flip it over, 3/4. X to the 4/3. And here's where we are, minus 5 times, and then 4/7 plus 1 is 11/7. 1 over 11/7 is 7/11. X to the 11/7, and then plus e. All right, one more step to clean up, and I think we'll be done. We just need to put some numbers together, like we need to multiply that, we need to multiply that, we need to multiply that. And so we'll have 1/3 x to the 3rd minus 2x to the 3 halves plus 3x to the 4/3 minus 35/11. Can't do anything with that other than just multiply them. Plus c. There we go. That's it. So the point of this example is just to get you used to the idea of the plus 1 stuff, right? Now there's some good news in Cal 2 when it comes to finding antiderivatives, which, by the way, we are going to be trying to find antiderivatives of functions until the end of September, I believe. I take that back. Yeah, September. Well, It'll be October 3rd will be our last day of finding antiderivatives. So we've got the next 4 weeks pretty much almost of just trying to find antiderivatives of functions. So the good news is that you can check your answer, right? How do you check your answer to see if it's right? Just take its derivative, right? If you take the derivative of this, you better get back this. I don't want to do each one, but let's just grab that one, see if that one's right. So if I take derivative of this, the 4/3 comes out, the 3's cancel, you just get the 4, right? So I've got a 4 there, great. And if you subtract 1 from that power, you get 1/3. So you've got that. You can check each one of them, it works. We good? Okay. I have a feeling that a lot of you have seen this. I teach a Tuesday, Thursday class, right? So they are now ahead of you all because we had the holiday. And I asked how many of them had seen the power rule and stuff. Everyone in the class except one person. So how about in here? Has anyone not seen the power rule? Not seen the power rule. So everyone has? Okay, good. So we're just taking our time. Don't worry. If you feel unchallenged, don't worry. Enjoy it while you can, all right? So how about this? I'm going to write something down here. Don't write it down, but I'm going to write something down. I want you to tell me what I did. Yeah, so all I did was I said, hey, look, this is x to a power, x to a power. Well, this is a constant. And we didn't really talk too much about this, but what's the antiderivative of a constant? Constant, and then just add an x to it because the derivative of that, the x will go away, right? And then I took the antiderivative of that and I just put it all like this, right? You think it's right? Why not? Do what? I have to bring the x to top, but why wouldn't this work? I mean, yeah, right, let's check our work. So if I checked our work, right, I would take the derivative of this times this minus the derivative of this times this all over this squared, right? It would be a mess, and I can assure you if you work it out, it's not going to be that. So when you do antiderivatives, if you have a quotient, you cannot just do top and bottom separately. Look, somebody is going to do this. I promise you. I've been doing this too long. Somebody is going to do this on the test. They're just going to take the antiderivative of top and bottom separately. Okay, this is a huge mistake. If the problem's worth 10 points, you would lose 9. I give you 1 point for showing up. Okay? But you'd lose 9 out of 10 points if you did this, because that's a fundamental lapse of what's going on. Understand? All right, so instead, the only way we can find the antiderivative of this is if it looks like x to a power plus or minus x to a power plus or minus x to a power. That's what we need. So we're in luck because I made this problem special for us. We have one term in the denominator. So you can split it into 3 different fractions. Right? You can split this into the x squared over x minus the root x over x plus the 7 over x. You can only do that because there's a single term in the denominator. Now you said you could bring the x up, so bring it up as like an x to the negative 1 and then multiply it through. Is that what and that will give you the same thing. Yep. Okay, now simplify. Notice I have not taken the antiderivative yet. I'm just going to simplify this. This is x minus, now maybe I should have written this one instead of root x. Maybe I should have done x to the half there, because I'm going to use properties of exponents here to get this one. When you have x to the half over x to the 1, how do you do that? Just subtract 1/2 minus 1, which gives you x to the negative half. And so I'm going to write that just the way it appears. X to the negative 1/2 is that piece. And then the last one, I could bring that up, x to the negative 1, right? But remember with the power rule, if it's negative 1, it's a special case. So I already know that the antiderivative of that's going to be the natural log. Okay, I already know that because it's x to the first power on the bottom. So I'm just going to leave it, but I'm going to write a little different. I'm going to go like this. That's still the same thing, right? All right, now we can use the power rule. Now you can. So this equals, no more integral sign, antiderivative of x is 1/2 x squared. Right? You're going to take the n is 1 there, so you go 1 over 1 plus 1, x to the 1 plus 1. And then on this next one, let me go into more detail. I'll have minus, and then I'm going to have 1 over negative 1/2 plus 1, x to the negative 1/2 plus 1. And then plus, any questions on that middle one? 7, and then what? Natural log. Natural log of x. I'm going to use the absolute value. And then plus c. This all right? Okay, negative 1/2 plus 1 is 1/2, but 1 over 1/2 is 2. Minus 2, x to the half. And then plus 7 natural log x plus c. That should be it. Now, if you're like looking in the back of the book for an answer, they might rewrite this as the square root of x, but it's correct, right? It's correct. Questions? So if we have a single term on the bottom and multiple terms on top, we can try splitting it up. Next example.
Can you have like example for ln where you get the operator to have for like setting x inside of it?
As the antiderivative?
Yeah.
Oh yeah, absolutely. Yeah. We will start to do something like that today. Yeah. The inside part we call the argument. Argument. An operator is kind of a name that we reserve for things that do things to functions. Like taking the derivative of something. The process of doing that, the derivative, is called an operator. It's called the differential operator. It operates on functions. See, functions usually take in numbers and spit out numbers. So we reserve the word function for things that do numbers in, numbers out. But things that take functions in and do something to them, like take the derivative or antiderivative, we call those operators. The inside of a function is called the argument.
Okay.
It's just language, but yeah.
Thanks.
Uh-huh. Okay. Can we split that one up like the last problem? No, because we have two terms on the bottom. What about tangent?
Isn't it like hyperbolic tangent?
Okay, so at least the neurons are firing correctly. I mean, well, they're firing. I think what you're seeing this arctangent of x. Okay, I believe I told you all that this was an important one to remember. This is going to come up a lot in this class, all right? The derivative of arctangent x is 1 over 1 plus x squared. Just burn that in, okay? So I think what you were saying is you kind of see the 1 over, you see the 1 plus x squared there. Okay. So if you see that, what could you do then? Maybe.
Substitute it in as 2 plus x squared times the arctangent of x.
Okay, so hold on. You're saying, could we do like 2 plus x squared times 1 over 1 plus x squared? Like that, just kind of rip it off, like rip the fraction apart like this?
Yeah.
And then this right here, the antiderivative is arctangent. And then this is just like power rule. Product. Let's act like that's what it was. Let's actually do that, and let's see it's not going to work. Remember we couldn't do division a second ago? Because quotient rule in Cal 1 screws everything up? Same thing here. We have a product. You can't just break it into a product and then do the antiderivative of each one. Let me act like I did that. Okay, I would take the antiderivative of this, which would be 2x plus 1/3 x squared, or x cubed. Do you agree that's the antiderivative of this? Okay, and then I'd say times and then arctangent of x. Maybe that's what it is. It's -9 on a test, but it is what it is, right? I understand what a student who did this, I understand what they did, right? Plus c, okay, -8.5. All right, so now let's check it. What's the derivative of this? Well, it's a product rule, right? So we have to take derivative of this, okay? Derivative of this is there, great, right? But then times what? So that would be 2 plus x squared, then times arctangent x, right? That would be, and then plus derivative of arctangent, 1 over 1 plus x squared, times 2x plus 1/3 x cubed, blah, blah, blah. And this is not even close. Well, I guess you could argue it's close, but this doesn't have any arctangents in it, right? And it definitely doesn't have 2x plus 1/3 x cubed either. So that's no go. Not happening.
If you treat the numerator like a coefficient,
How do you mean like a coefficient?
like when you have like 3x something, you carry the 3 in front of it.
Like it just comes with us? The question is, can I treat the 2 plus x squared almost like a constant and just take the antiderivative of this part and just bring this for the ride? And unfortunately, because it has x in it, you cannot. This has to be a constant by itself, all right? So do you all agree we're a little bit jammed up here? Yes? Like it's not, from what we know so far, this is not falling into the pattern of what we know how to deal with. We see there's an arctangent perhaps in here, but we can't quite get it where we want it. And I think this is the first problem that I'm going to show you where you start to see what I mean by this class is about some sort of weird instinct and just kind of doing strange things instead of the very mechanical process of product rule, quotient rule, chain rule. You know, those were all processes that were easy to follow relatively, but this is not necessarily that easy. So, you ready to see it? Check this out. This is just clever, all right? It's just clever. Watch this. I'm rewriting 1 or 2 as 1 plus 1. All right? Is that legal? Yes? Now, right here, I'm going to split my fraction. So I'm going to write 1 over 1 plus x squared plus 1 plus x squared over 1 plus x squared dx. Is that legal, what I just did? Well, yeah, check it. Do these have the same denominators? Okay, if I put these together, then I would just do this plus this and this, right? So I go back to this. And then that's obviously this. So that's all good, right? But what is this? What is that? 1. Now you have two terms, don't you? This plus this. Now you can take the antiderivatives independently. And what's the antiderivative of this? Arctangent of x. And what's the antiderivative of 1? Just x, 1x or x, and then plus c. And that's it right there. Right? That's kind of strange, isn't it? Like, how do you see that?
Just seems like cheating.
It does, right? I said it was clever. We'll call it cleverness as opposed to cheating. It's being smart with the algebra, and it's seeing it before it's happening. Do you see that? Like, I had to see that. So, one thing I'll say is, in this class, when you're doing your homework, I've told you, try to avoid just watching my homework solutions and just sitting there and watching them being like, okay, because really the critical part for you is taking that first or second step on your own. If you watch me do it, you don't get to fall and get back up. And in this class, you will fail more times than you succeed when you're doing your homework. I mean, I expect that you're going to do a problem, you're going to crumble it up, and you're going to start over, many, many, many times in this class. That's part of what it takes to understand it and to get good at it. All right? All right, so that worked, but it was cheating clever, right? So let me show you another way to do the problem that's maybe a little more in line with, like, it might feel more mathy to you. How about if I did this? Just to start the problem, let me take that expression. Now, you may not like this, but it's something that I think seems more, like I said, mathy to you. What am I about to do? I'm going to do long division, right? This is this divided by that, right? So if I take this and divide it by that, I can do long division. So I rearrange it, I put it in descending order, and then I do my long division. Now you will have to do long division in this class later on, so we may as well just do this. How do I do this again? I look at this and I say, what do I need to multiply that by to get this? So what do I have to multiply it by? 1. So I put a 1 here, and then I multiply 1 times this, x squared, 1 times that, I get plus 1, like that, and then what's the next step? Subtract it, right? So you come in here and you change the signs. This becomes minus, and then subtract down. And what do you get? 1, right? And then you ask yourself the question again, what do I have to multiply x squared by to get 1? And you can't, right? So that's our remainder. So we put R1, no, this is not grade school anymore, right? So we say, no, we go plus the remainder over the divisor. And that is this, right? Does it matter that it's x squared plus 1 instead of 1 plus x squared? No, because it's addition, so that doesn't matter. See that? There's 2 ways you could have got to it. But this way is definitely more elegant, and later on when I'm doing problems, you'll see me do this other times, and it's just, now you know, okay? Now you know. Like, this sort of thing is within the realm of reason, all right? Yes?
So it's okay to think, like, if I see something like that where I can't split it, just think, okay, long division. It's okay to do so I can do long division every
Yes.
time?
You can attempt long division. Yeah, so I can't give you a cookie cutter way of doing anything when it comes to antiderivatives. I mean, the best I can do is like the power rule. I can say with the power rule, if you see x to a power, just use the rule. If it's antiderivative of sine, you already know that. But anything else, it's more like you have to have everything be exactly a certain way for me to tell you, yes, that will work every time. Because long division will not work every single time. It depends on the expression itself. If I throw a sign in there up on the numerator, like long division's done. You know what I'm saying? All right. Or if I make one of these a root. Like, let's say this was 2 plus root x, right? That's why we have to spend a month trying to figure out how to take antiderivatives, because it just takes so much effort to do these things. All right, we good? Questions? Linear motion. This is about things moving in straight lines, all right? objects that are moving in straight lines. How many of you recall this from Cal 1? And it will depend on your teacher, really. If you have a graph that puts distance versus time on the graph, so time is the x-axis and the y-axis is distance, then if you have some function here, that curve would represent where an object is at every point in time. So let's say we have a little car, you know, it starts here and then it starts moving and maybe it speeds up and then slows down, then speeds up and slows down. And we have a graph that shows how far it's gone at every point in time, right? Then if you take the derivative of this, if we call this right here s of t, which is the position function, then if we take the derivative of it and graph the derivative, what would that give us? I'll give you a hint. This is time. But the derivative will not give us distance anymore. It'll give us what? The speed or velocity, right? So that'll be some different curve, you know, whatever it looks like. Who cares? Right? This will be velocity. Is there a difference between speed and velocity? Yes. But that's more of a physics thing, right? Velocity has to do with two things. It's the direction and also the displacement. So the speed is more like just the displacement over time as opposed to what direction you're pointing. The reason why it doesn't matter in this case because it's a linear motion, straight line motion, all right? Okay, so that would be s prime of t. And we have a special name for that function. We call it v of t. That's a v, not an r. So this is velocity. And then what happens if I take the derivative of the velocity function? We get acceleration. I'm just going to put accel. And this graph, whatever it looks like, would be the second derivative of the position function, and then that would be a of t. And this is your acceleration function. All right, did you all see that in Cal 1? Position, first derivative gives you velocity, second derivative gives you acceleration. Anyone not see that in Cal 1? Sorry. No? Okay. So that's a nice result. Now, since you haven't, is there anyone who has not? Just you?
Disabled Veterans of America.
What's that?
Disabled Veterans of America. DVA.
DVA? Oh, okay. I'll let you, that's your thing. I don't want to say anything about anyone. In 2018, you can't say anything about anyone. I can't even say certain words. Okay, let's talk about why the derivative of this is velocity, right? Because I want to clarify this for you and for everybody, because you may not have actually thought about it too much. When you talk about speed, the definition of speed, very layman's definition, is distance over time, okay? It's the amount of distance you cover over a certain time period. That's really the average speed of something. So when you take a derivative of this function, right? When you take a derivative, like let's say we go and we take a slope of a tangent line like this. When we take the derivative, it is your change in y divided by your change in x, right? Now, what's y measured in? Distance, right? So it's your change in distance divided by your change in time, which is exactly speed, okay? So the derivative of position gives you velocity. Now, what is acceleration defined as? Acceleration is your change in velocity over time. That's the definition of acceleration. Well, if you take the derivative of this time it's change in velocity over change in time, and that gives you acceleration. Does that kind of make sense? Okay. All right, but we're not interested in going this direction, okay? This was Cal 1. What we want to do is go the other direction, all right? So we want to start out with acceleration, and think about this. This is actually pretty profound. If I tell you the acceleration of an object at every point in time, does it seem possible to then be able to tell me exactly where it was at every point in time? That seems like that would be very tough, right? Like all I tell you is like, hey, look, at this point in time, even this, if I tell you how fast something is going at every point in time, do you think you can tell me where it is? That doesn't seem reasonable, does it? Does it or not?
Not really.
Not really. I mean, look, I'm telling you right now that there's a car driving San Antonio going 50 miles an hour, right? Where is it? Right? I mean, that's really what I'm kind of saying. And it turns out that we cannot go from here backwards, or even from here backwards, with just the antiderivative. We have to have something more, all right? And that's because when we do an antiderivative, what do we always have when we do that antiderivative? That plus c. We get a family of curves. We actually have to nail that curve down somehow to figure out which one out of the family it is. And then to go back again, we have to nail that one down again, all right? So let's do it. Let me show you how this is going to work. I'm going to give you an acceleration function. And let's see if we can do it. Okay, you know what? Before I do it, I wonder if anybody has seen this before. It would have been probably college algebra or a physics class. Has anyone ever seen that equation before? Or that function? Where have you seen it? Do you remember? Physics? College algebra? Do you remember where in physics? Like what it has to do with? Or
It's an acceleration.
it's not acceleration. Well, you could say that in some way. It's not an acceleration function though. This is usually in like kinematics, one of the kinematic equations, but this tells you that if you take an object on Earth, okay, we have to be on Earth, and you take out air resistance, if you drop an object on Earth, this will tell you exactly where that object is at every point in time. So there are a few things you have to know. D naught is your starting height, okay? That's the height at which you're going to drop the object from. And let's say, 0 is what, sea level, or you could always say 0 is something, right? 0 is the ground right here. Then maybe we're, 50 feet up right now on the 3rd floor. Who knows, right? But this will be the height relative to 0 that you're starting the drop from. This right here is your starting, what do you think? Velocity. And that means I can drop it, right? Or I can throw it. If I throw it, it's going to get there faster, right? Or I can throw it up, which means it's going to take a little longer, right? This number controls which of those happened. If you just drop it, V0 is 0. If I throw it down, this is some positive number. If I throw it up, it's some negative. No, I got that. Yes, I got that right. Negative up, positive down. Okay? Got you? Got it? And then this right here never changes in the formula. And the reason this never changes, we're about to see. All right, you ready? I just want to see if anyone's seen that. I'm actually going to come up with that now. All right, here's your example. If S of t, not S of t, A of t, if A of t is negative 32, find S of t. So I've given you an acceleration function, okay? I've given you a constant acceleration function, negative 32. That means the acceleration is always the same, right? No matter what you plug in for t. That's like gravity. What is the acceleration of gravity, my physics people? What's the acceleration of gravity?
9.81.
Negative 9.8 meters per second per second. You hear that in physics. If you convert that over from meters per second to feet per second, it's approximately negative 32 feet per second per second. All right, so what I've done up here, even though you didn't know it initially, is I've actually put the acceleration of gravity as our acceleration function. All right? Now, let's see if we can get a position function from that, which would tell us where an object is at every point in time, right? Okay, let's do it. What would v of t be? Well, that would be the antiderivative of a of t with respect to, what's our d here? D what? dt, not dx, see? Because our independent variable is t. All right, now what is the antiderivative of negative 32 with respect to t, not x? Negative 32t, right? Negative 32t plus some constant, right? That I don't know. And that's the best I can do, right? I don't know what c is at all. No, I have no other information in the problem given to me. All right, well, how do we get to the position function? The position function, what we need to do is find the antiderivative of the velocity function that we just found, right? So let's find the antiderivative of that velocity function. So in those three pictures I drew, we just took one step back, and now we're going to take the second step back, right? So what's the antiderivative of negative 32t? Negative 16t squared, right? That's because I ignored the negative 32. The antiderivative of t is 1/2 t squared. And then I hit the half on the 32, negative 32, and got that. Plus, okay, what's the antiderivative of some constant? Constant t. Plus some constant, right? I'm not going to use c again. I'm going to use a different constant, so I'm going to use d. Got it? This is the physics equation right here. Negative 16t squared plus, now this constant I'm saying here is the starting velocity, right? It's the velocity I start with. Let's try and understand why this number in front of the t is always your starting velocity. You see this right here? That's my velocity function, right? What's happening at v of 0? What's happening in the very beginning? What's my velocity? Well, plug 0 into that, and what do you get? C, don't you? So shouldn't this number right here always be my starting velocity? So let's call it v sub 0. Make sense? And then, why is this my starting height or starting position? Well, what's s of 0? Well, if we go to the position function, plug 0 in here and 0 in here for t, you get d, don't you? So that number right here will always be my starting position, so I'll call it d sub 0. And there it is, right? That's pretty awesome. That's pretty awesome, because if you want to go to a different planet, all you have to do is change that number, right? If you go to the moon, your gravitational acceleration changes, but you can still drop something on the moon and tell exactly where it's going to be at every moment in time, because all you're going to do is just antiderivative twice, right? And you have your kinematic equation for the moon. So this is the only thing right here. This is the only thing that has to do with the fact we're on Earth. Everything else would be the same. So on the moon, this number would change. Make sense? It's pretty cool. So all objects dropped from any height on any planet, if you take out air and maybe some other factors like that we're just kind of throwing out the window right now, then the model for that falling object is always a parabola. Always. It's always a quadratic function, no matter what. But you have to have constant acceleration, right, for that to happen? All right, let's take the same problem here. I want to take this same exact model. We're going to be on Earth. But I'm going to give you some more information. So let's start here. If a of t equals negative 32, comma, v of 1 equals 4, comma, s of 2 equals 14. Find s of t. Okay, so I want you to understand what's going on here visually, because this I think is pretty cool. I'm going to draw 3 graphs. You don't need this for the solution. I just want, again, for you to understand what we're doing. Okay, here's